Hello, today I'd like to share a project on model-free cyber-resilient coordinated inverter control in a microgrid. With the increasing integration of inverter-based resources or IBRs in the power system, there's a need for new control techniques for both grid forming and grid following IBRs. This is because a fully inverter-based power system has issues such as low inertia and sensitivity to disturbances. One control method to improve the transient response of IBRs is called set point automatic adjustment with correction enabled, or SPACE, and it works by modifying the input set points of the IBRs. Coordinated SPACE expands on SPACE by incorporating communication between IBRs. This allows the IBRs to exchange their error values and support each other during transients, improving the overall performance of the system. However, the use of communications in C-SPACE exposes the IBRs to cyber attacks. This pseudocode gives more details on GFL control with C-SPACE. As you can see, the error values are modified using the predicted error values in space. And then in C-SPACE, the set points are further modified using the error values exchanged from two other IBRs in the power system. There are many different types of cyber attacks, but in this project, we focus on false data injection, or FDI attacks, and denial of service, or DOS attacks, on the input set points of a GFL IBR. In an FDI attack, or in a sub-FDI attack, the input error is set to a set value after a time t attack. In a ramped FDI attack, the input error is ramped linearly to a set value over the time td. And in a random FDI attack, the error value is set to a stochastic signal, which becomes either 0 or 1 randomly on each time step. Lastly, in a denial of service attack, attackers prevent communication among IBRs, forcing them to continue using the last set of error values received. If the error values were received during a transient, they may be severe, causing overvoltage or undervoltage in the system. To test our proposed method, we developed a test bed, which includes a computer running PSCAD software, a network switch, and two Raspberry Pi computers. PSCAD simulates the power system layer, which is a modified version of the 14-bus secret grid. The power system exchanges data with a Raspberry Pi server through the network switch. Lastly, a malicious Raspberry Pi launches cyber attacks on the Raspberry Pi on the network switch. To detect FDI and DOS attacks, we developed a long short-term memory, or LSTM model, which is a type of recurrent neural network. A bidirectional LSTM is a modified version of LSTM, and we use it to mitigate the attacks by estimating the non-attack error values. After an attack is detected, the falsified error values are replaced with the corrected prediction values to mitigate the adverse effects of the attack. Because we implement the detection and mitigation algorithms at the remote terminal unit level, they operate on local measurements and can prevent error values from reaching the IBRs, can prevent falsified error values from reaching the IBRs, as you can see in this diagram. When an attacker falsifies the error value and it's sent out to other IBRs, the detection and mitigation in the RTUs send the corrected error values to the IBRs instead of the falsified values. We tested the performance of our method through several case studies. In this first case study, you can see a step attack on the real power outputs and a ramp attack on the reactive power error outputs of four IBRs 1, 4, 12, and 14. At the top is the attack detection signal, showing when the attack is detected just a few milliseconds after the start of the attack. And then, as you can see, the real and reactive power error values are quickly restored to normal, preventing undervoltage in the output voltage. We also tested a random attack on IBRs 1, 2, and 4, and you can see the simulation results for IBR 1 here. Here, the detection takes longer because the model has not been trained on random attacks, but it still manages to successfully detect the attack, correct the error values, and restore the voltage to normal. It also reduces the frequency violation in the system. In this work, we've proposed a model-free control method, which adds cyber resilience to the C-SPACE algorithm. Our method is able to detect and mitigate a variety of attack types, including DOS and FDI attacks on the Seagate 14-bus North American microgrid. We also verify the performance of our method and the realism of the cyber attacks using a network in the loop testbed created using PSCAD, a network switch, and two Raspberry Pi computers. Thank you for listening.